Okay. So before I get to the next chapter in my presentation, I want to write down a definition that I gave already in passing, but I didn't write it down. Oops. So if we have a valued field, we call it Henselian. My God. Will be there anything left? If, and now I'm referring to Graham's first lecture, if the valuation ring is Henselian, which means, and he wrote down Hensel's lemma. Which I will abbreviate as HL from now on, holds. And equivalently, well, that's quite surprising that these are equivalent. V has a unique extension to the algebraic closure of L. So Graham mentioned already there are several equivalent formulations of Hensel's lemma. Actually, when you pass to field theory, Henselian fields, there are certainly more than a dozen, maybe even dozens of equivalent formulations. And so we know Hensel's lemma as a slight generalization, Newton's lemma. We know the multidimensional versions of these two. We know Krasner's lemma. We know the slightly mysterious Hensel-Richlich lemma, which was used by X and Cochin in their famous work. And okay, so you can look up all these. Now I could also write reference book. Well, let me write it this way. So this is a book that I hope to finish in the not too far future. And but there are several preliminary versions of several chapters already online. So if you go to my personal website, you will find these online chapters, and especially there's a chapter on Hensel's lemma, giving all these equivalent forms of Hensel's lemma. Okay, now I come to chapter 5 of my presentation. Oh, okay, I should also say the Henselization, which I will write like this, or just L to the H, as I did over there, is the minimal, or a minimal Henselian extension, in the sense that it embeds into every other Henselian extension of L. I mean, evaluation preserving embedding. Okay. Chapter 5, structure of valued function fields. And function fields, I mean algebraic function fields, and I will always abbreviate it like this now. Okay, and what I want to do is I want to give you an impression of the obstruction the defect causes in the structure theory. Okay, so we take an algebraic function field with evaluation, and we look first at the case where this extension is immediate. And I recall that immediate, let me write it out for once. Immediate means that the value group and the residue field on both f and k are the same. Yeah, so, and additionally, we look at the case that the transcendence degree of f over k is 1. Okay, now, what we can do is we can take a transcendental element. Yeah, so x transcendental. And we can look at the respective Henselization. So take a Henselization of f, and in that you find the Henselization of kx. Now this was immediate. So in particular, this is immediate. Henselizations are immediate extensions. And it follows that this extension is also immediate. So that means that when we look at ramification index and inertia degree, they are both 1. So that means that the degree here, because the extension here is unique, this is Henselian, the degree is equal to the defect. Now, if we assume that the residue characteristic is 0, then we get that d is 1. And so we get that fh is equal to kxh. Or in other words, f is contained in the Henselization of this field. Okay, and this leads to the following definition. So this valued function field is Henselian rational. So it's, so to say, Henselian after rational after going to the Henselization. And now let's do this definition in general for any transcendence degree. If there is a transcendent space is T, of f over k, such that f is contained in kt Henselized. Yeah, so if you take L to be kt, okay, you get your f into this first step here, Henselization, which is the absolute decomposition field, as I showed you in my scheme last time. Now, what if, in this case, yeah, if the characteristic of the residue field is bigger than 0? In this case, well, if this characteristic is P, the defect is always a power of P, then this D can in fact be any power of P. So we are, in this moment, we don't know whether this guy is Henselian rational or not. So in positive characteristic, we would have to try to find a better x. But that is not always possible. So, as I told you, the case somewhat complementary to immediate is the case of Apjanka valuations. And now let's look at this special case, f over k, algebraic function field, V and Apjanka valuation of f over k. And so in algebraic geometry, you usually look at valuations that are trivial on k. Which means that V restricted to k is trivial. Yeah, and kV you can, modulo equivalence of valuations, you can assume that this is k. And we also already mentioned that if we have an Apjanka valuation, we have this wonderful property that the extension of the value groups and the extension of the residue fields both are finitely generated. Which gives us here that V of f is finitely generated, and also this here is finitely generated. So let me say here finitely generated, and that the extension of fv over k is finitely generated means that fv over k is again an algebraic function field. Okay, so we can do the following. Can choose finitely many elements xi in f and yj in f such that our V of f is z V of x1, direct sum up to z V of xr, and that k fv is, okay, we choose the y's such that we get the transcendent spaces generated by the residues. So k adjoint y1v, this is the residue of y1, up to ysv, and then something algebraic. And now when we add an assumption that we always need, we will always need later, so general assumption that fv over k is separable. So then we only need one algebraic element here. So, well, algebraic geometers often tend to work over perfect fields. So if k is perfect, this is automatic, the separability. Okay, assume for now that actually this function field here is rational. So we don't need A. And we set a subfunction field f0 to be k generated by these xi's and yj's. Okay, so we have K, F0, and F. And by setting this here, we see that, okay, in the value group, yes, we have all elements in there that generate the value group. We have all elements that generate the residue field. So this is immediate. Yeah, and we play the same game as before. Take a Henselization here, take the Henselization of this in the Henselization of F, and we get that this here is immediate. But here, the valuation is Apjanka. And remember, we had a theorem that said, okay, if the valuation on the base field is defectless, well, but here the valuation is trivial. So it is defectless. So by earlier theorem, we have that this is also defectless. And now what we need is a general theorem. LV is defectless if and only if its Henselization is. And so we get that this guy is defectless, but this was immediate, so E and F is 1. So we also have D is 1, which gives us that FH, why do I write it here? FH is F0H. And by the choice of our elements here, this is in fact a transcendence basis because, okay, so these values were rationally independent, these values, these residues algebraically independent. So this is a transcendence basis. And so what we get is, the result in this case is we get again Henselian rational. Okay, so let's not forget about the case that we have possibly an A here, so that our function field, the residual function field, is not rational. In that case, if A is needed, then with very similar arguments, that we can choose A such that F sits inside KT, but not the Henselization. But since A is this is a separable extension of this by our general assumption, the separable extensions of the residue field, they happen here. So we are inside the absolute inertia field. And we defined F over KV is inertially generated if there exists that side. Transcendent spaces T such that F sits inside KT, absolute inertia field. Okay, so we see when we have an Appianka valuation, there are no defects. Fine. Yeah, and we get this really strong structure theorem. If we are in the immediate case and the residue characteristic is not 0, we don't know what to do, because defects may very well appear. Somehow, in the end, we will have to try to work around the defect. Okay, now these are two complementary cases. So what about the mixed case? Yeah, you have this function field over K, and we want to get a function field in between that looks like the one that we had here by taking now x1 to xr. We cannot take them as generators of the value group. The value group may not even be finitely generated. But we take x1 to xr in F such that their values are a maximal system of rationally independent values. Because the rank is still finite of the value group of F. And we take the y's well, now they should be in the valuation ring such that their residues form a transcendent spaces of this extension. Now, in this case, we cannot say that this is an algebraic function field. It might be not finitely generated, but still the transcendence degree is finite just by the Appianka inequality. But now in the Appianka inequality, the mixed case means that, well, here we have an Appianka valuation, but if the whole thing is not Appianka, then we have bigger than the transcendence degree, Fv over K, plus the rational rank of V of F. So that means the bad case, the mixed case, is where this is still transcendental. And, well, especially when the value groups or the residue fields is not finitely generated, we only know that V of F, by our choice of the y's and the x's, V of F modulo V of F0 is torsion. And we only know that Fv over F0V is algebraic. That's all we know. Yeah, but the case where we had a hope that we could do something was the immediate case of transcendence degree 1. So we can work on the F0, that's fine, but then we have to somehow go up to F, and we somehow want to reduce to case 1. And we do that by enlarging our F0 and thus also F. So we will probably only get a nice structure theorem after making F bigger. And the second thing is that we need is we have to reduce to transcendence degree 1. I call that slicing. Yeah, and that is also not clear how that can be done. And it also in the end means, again, enlarging our F0. Okay, the effects of which I will tell you in the next chapter, which is the chapter on local uniformization. Okay, the background for that is resolution of singularities. Which was proven by Hironaka in 1964 for characteristic 0. And since then, although many people, including Hironaka himself, have worked on it, the positive characteristic case is widely open. How widely, we don't know, because the devil is in the detail. And although Hironaka has a manuscript on his website, there has been a delegation of experts checking that proof and have found gaps in it. So things are evolving, but we are not there. Now, resolution of singularities, what does it mean? We have a variety with singularities. And we want to associate to it a new variety by rationally equivalent. More precisely, but I'm just going to mention that we want to have a morphism here, which is a proper birational morphism. This is too high for me. Well, in a double sense, yeah. Okay, so birationally equivalent such that this here is regular. Loses all the singularities, all of them, globally. So if we are too dumb to solve a problem globally, we at least try to solve it locally. So local uniformization means something like get rid of one singularity at a time. Meaning, okay, we grab a singular point and we want to find v prime such that this point becomes regular. Now this is nonsense what I'm saying, because that point in v is not a point on v prime. So we need to set up a correspondence. Between points on v and on v prime. And that's Zariski's very nice idea how to do that. And to introduce you to that, let's think for a moment about what a variety actually is. So variety V. Okay, so you have a system of polynomials fi in x1 to xn and m many. So naively, a variety is the zero set of this system in, okay, and not quite so naive, let's take L to the n, where L over K is some extension. Okay, so now we can take such a naive zero and we can evaluate at this zero, we can evaluate our polynomials, not only these, but the whole polynomial ring, and that we call an evaluation homomorphism, from k x1 to xn to L. Now, the ideal generated by my polynomials in the system, certainly in the kernel, of this homomorphism, so it induces a homomorphism from this K, this polynomial ring, modulo this ideal to L. And this guy here is what we call the coordinate ring. Okay, now we could say that the points on our variety are these homomorphisms. And an even more modern point of view, the homomorphism is certainly described by the kernel here. So you associate the points with prime ideals. But I don't want to go so far. Let's stay with this view that the points are homomorphisms of the coordinate ring. And now we are able to set up the correspondence. So we have KV, and we have some new variety V prime. We look at the homomorphisms here. How do we associate the homomorphisms here? Okay, so okay, so V and V prime birationally equivalent is actually equivalent to that these guys here, let me introduce that first. So we say that K, my God, KV is the quotient field of my coordinate ring, and this is an algebraic function field over K. Okay, and that these are birationally equivalent means that their function fields are actually the same. So from this you can get the idea, okay, here you have your homomorphism, go up to the function field, it's the same as this one here, and go down here. So extend your homomorphism to a homomorphism of the quotient field. Well, impossible, because in most of the cases, the homomorphism here will send elements to 0, so their inverses have to go to infinity. And that's the idea where places come in. So we want to extend to something up here that was a homomorphism here, but allows the values infinity on the quotient field. Definition. A place is a map, or I should say on L, is a map from L to somewhere, and this somewhere we call LP, but you allow infinity such that this map P is a homomorphism on a subring OP of L such that for all x in the field, x in OP or 1 over x is in OP, which means that OP is a valuation ring of L. Now, here we have the definition of a valuation ring. And outside of OP, and here we have a phenomenon, places are traditionally written from the right, in contrast to other maps, because it comes from these evaluation homomorphisms. And one just dropped the parentheses, so one writes it like that. AP is infinity if A is not in the valuation ring. So that's a place. And so what we do is we have a homomorphism here, we extend it to a place here. There are many such extensions. So over every homomorphism there are often infinitely many places, but that doesn't matter too much here. Okay, and now what we want to find a V prime such that, first of all, well, we do that to get another homomorphism here. So P restricted to this ring here must be a homomorphism, which means that this ring lies in the valuation ring. And secondly, well, our goal is to have a regular point. So that means we get a homomorphism. P restricted to KV prime is a homomorphism, and so we have a point here. The corresponding point is regular. Not so good. Don't like that too much. And I will tell you in a moment why I don't like this. In many situations it's the same, but there are situations where this is actually stronger. I want smooth. What does smooth mean? That means that the implicit function theorem I will abbreviate by AFT, holds in this point. Okay, and that's good because the implicit function theorem now, because I'm looking for smooth, now I can do valuation theory, and the background is that the implicit function theorem is very close to, so to say, a reformulation to Hensel's lemma. Actually, multidimensional Hensel's lemma. And meaning that, okay, the smoothness is practically can be formulated as the hypothesis of the multidimensional Hensel's lemma. Okay. What does this have to do with that side here? Theorem. Hagen-Knaf, my co-author, and myself in 2009 proved that that a place of f over k admits local uniformization, meaning that v prime as above exists. This implies that the valued function field, now v is the valuation associated to the place p. Remember, okay, we have valuations, we have valuation rings, and we have places. That's a trilogy. They all correspond to each other. And if we have a place P, okay, the corresponding valuation will be denoted by Vp. This guy is inertially generated. Okay, and another definition, we say that the place P admits elimination of ramification. And that we abbreviated by ER, if exactly that is the case, f over k Vp is inertially generated. Now, elimination of ramification is weaker than local uniformization. I once asked Michael Temkin whether there is a way to prove directly local uniformization from elimination of ramification. So what's the difference? Is elimination of ramification easier? And he smiled and he said, oh, he thinks that the one who can prove elimination of ramification can also prove local uniformization. Okay, and that's the last result for today. Zariski in 1940. Every place of f over k with the characteristic of k being 0 admits local uniformization. Now, remember, so in this case where the place is trivial on k, k is the residue field. So we have residue characteristic 0, and remember that in residue characteristic 0, this is the algebraic closure if the residue characteristic of LV is 0. Yeah, so what Zariski had to do, he had to only eliminate the so-called tame ramification here. What we have to do when the characteristic of the residue field is not 0, we have all this bunch here. So in positive characteristic, we have to eliminate all ramification, including the wild ramification, and that's where the defect comes in. And that is much harder. And why inertially generated, and why do algebraic geometers call this the strict tensorialization? Because this here is the region where Hensel's lemma holds. And beyond that, as soon as we have ramification, Hensel's lemma as a tool breaks down. So we want to squeeze everything in the absolute inertia field over a field, of a rational function field. And okay, so I will tell you next time in which cases this has been done successfully and which theorems are behind that.